So for question 1, we're asked, given this information, what is the allowable torque if the shear stress should not exceed 50 megapascals and the angle of twist between the ends of the bar is not to exceed 1.4 degrees? So first we need to define what 50 megapascals is. So that means the allowable shear stress equals 50 times 10 to the 6 pascals. And the angle of twist, the allowable angle of twist, equals 1.4 degrees. But because torsion is, in torsion we use radians, we need to convert this to radians, which is pi over 180 equals 0.0244 radians. So first, we're going to see, so what you have to do is basically, you see what is the torque allowable based off of the shear stress, what is the torque allowable based off of the angle of rotation, and whichever one is lower, it governs. That means that's the answer. So first, torque equals 16 shear stress equals 16 times the torque allowable, which is TA, over pi d cubed. And the diameter that we're picking is the smaller diameter, d2, because the smaller the diameter, the more stress that occurs in that part of the bar. So if you rearrange this equation to find TA, the torque allowable equals the shear stress times pi times d cubed over 16. So once you plug in the numbers that you are given, which are 50 times 10 to the 6 pi, and the diameter 2 is 36 millimeters, which will be 0.036 meters, and then you're going to cube that divided by 16. When you calculate that, for the torque allowable based off of the shear stress, it will be around 458 newtons meters. So now we have to go to find what is the allowable torque based off of the angle of rotation. So with this, you use superposition because the angle allowable equals TA times the length of that section times the shear modulus times the polar moment of inertia. So the angle of twist between the beams will be the angle of twist of AB. This is A, this is B, and the angle of twist of BC, which equals torque allowable over shear modulus, and then you use superposition to do these. So L1 over J1 plus L2 over J2. When you rearrange this equation to find the torque allowable, it will be the allowable torque equals the shear modulus times the allowable angle over L1 moment of inertia 1 plus L2 moment of inertia 2. And once you plug everything in, this should equal about 218 newton meters, or around that. So that means that 218 governs, meaning that the max allowable torque in this beam is 218 newton meters. So for this question, you need to figure out how many cuts would you have to make in this beam in order to successfully analyze the shaft. So, well, in the shaft, in order to successfully analyze it. So the first cut will be between these two. Cut 1, because you want to know the impact of reaction force A. And then the second cut will be in the distributed load. And that is because this internal torque changes based off of where you are in this distributed load. So you need to figure out what that internal torque is. The third cut will be right after the distributed load and before this change in area. And the fourth cut will be after the torque, the concentrated torque applied inside of this changed area. So assume that the concentrated torque is applied at the end of that area. So these are the 4 cuts that you will be making. So this is the statically indeterminate problem. For this problem, I want you all to focus on the process, not necessarily the numbers. You can always plug numbers in, but focus on the process, because if you focus on the process, then the numbers really don't matter because you'll make some errors because it is a lot of algebra. So first, we want to develop the free body diagrams for the entire bar and any necessary individual sections. So from what we know, we can actually cut this into 5 sections. So we have cut number 1. And then we need to cut between B and C. We need to cut between C and D. We need to cut in between D and E because of the change in diameter of the shaft. And the final cut that we need to make is between E and F. Okay. So first we're going to draw a free body diagram for the entire shaft. So this is the impact of the reactive torque on F and the reactive torque on A. And then we have a distributed torque here, which is T of X, where X is this way, starting at 0. And then we have a concentrated torque at E, going in the negative X direction, the negative T direction. So right here. And T of X is 150 Newton meters per meter, and T is equal to 270 Newton meters. So now we're going to do the individual cross section. So for me, I'm going from the left all the way to the right. I'm not coming from the right and to the left at any time. So I'm going, for every cut, I'm going from the left all the way to the right, just for consistency in the answer. So cut 1 is between 0 and 1/6L, where L is 3 meters, so that means that this is 1/2. Is 0.5 meters, so. And then you have the internal torque 1 and your reactive torque at A. For cut 2, it's between 1/6L and 1/2 L. And the reactive torque, so this is taking into account the distributed load, but it's inside of the distributed torque. So what you have to do, because the distributed torque depends on X, this whole bar will be X, and where it's not applied is 1/6L. So we'll get into that soon. And the distributed torque, the reactive torque is actually distributed in between B and C. And then for cut 3, we're going to go all the way to D. which is 1/2 L X 4/6L. And you'll have a reactive torque 3, and a reactive torque at A, but also this distributed torque. And these inequalities are showing you where the reactive torque will be valid. So T1 is valid in between these 2 points of X, T2 is valid in between these 2 points of X, T3 is the reactive reactive torque in between these values of X. And this is T of X right here. And then cut 4 is between the reactive torque is impacting this section right here, 5/6L. And then you're going over a little bit between D and E. So the reactive at A, this is the internal torque number 4, which we'll find out is actually equal to T3, and the distributed torque here. And then for the fifth and final cut, you'll have it between 5/6L and the total length of the bar. You have the reactive torque, you have torque of cut 5, and then a newcomer is this concentrated torque right here. Let me put a torque symbol. This concentrated torque right here, T, and then your distributed torque right here in the area. So these are the individual sections that you need. So for the next question, I'm gonna have to erase the board, unfortunately. I have to erase the board, but I don't have enough space. But I'll keep the free body diagram for the entire one so we can create equilibrium equations for every section. Okay. So develop the equations of equilibrium, compatibility, and torque displacement. So first we're going to do the equilibrium equations. So I'm going to do the entire bar. So sum of torques is supposed to equal 0 for equilibrium. So if you use these, so 0 equals negative TA, because our x direction is this way, so our positive direction is that way. So negative reaction torque of A plus the distributed torque x minus 1/6L, because that's 1/6L and x will be this way. So how far along you go across x minus 1/6L. Minus T, the concentrated torque, plus the reactive torque at F. So my rule of thumb is to put the reactive torques on one side and the known torques on the other. So TA minus TF equals TX x minus 1/6L minus the concentrated torque. And just to plug in some numbers, this will equal 150 x minus 0.5 minus 270, which will end up equaling 150 x minus 345. So the reactive torques will equal that. And eventually x maximum, because our x of interest may be at 1.5, so x eventually will equal 1.5 meters. And then we'll plug that in there. So next we want to do, so this is the equilibrium equation for the whole shaft. Next we want to do it for the individual sections. So to figure out what T1, 2, 3, 4, and 5 are. So for number 1, it's the equilibrium equation, torque. The sum of the torque should equal 0. So it will be negative TA plus T1, because T1 is going in the positive x direction. All of our reactive torques are going in the positive x direction. And if you rearrange this equation, T1 equals the reactive torque. So for 2, 0 equals well, 0.5, but actually this should be 1/6. And then you add the torque that is based off of x. So that is T2x. So that means that T2x will equal TA plus 150x minus 1/6L. Oh, disregard this Tx, because Tx equals 150. I apologize. So that's the equation for 2. So now for 3, you'll have all of this, but x will equal 1.5. So equals negative TA plus 150 x minus 1/6L plus T3. So T3 will equal TA minus 150 times, because it's after the distributed is actually x will be 1.5, and then you continue, so x is at 1.5. So if you put 1.5 minus 0.5, this equals 1 actually. So it works out, so it will be T3 equals TA minus 150. And then, like I said earlier, because it's only taking into consideration the change in diameter, the internal torque is actually the same for T4. So T3 equals T4, which equals the torque minus 150 times 1. And the last one, the fifth equilibrium equation, is 0 equals negative reactive torque. So I'm going from this side all the way to here, minus 150. And again, we're going to do it like this, where x is 1.5, and 1/6L is 0.5 because L equals 3. So it'll be 1 minus, and then it will be minus 270, which equals, plus the reactive torque, number 5. So the reactive torque 5 will equal TA minus 150 minus 270, which equals TA. This will be minus, this will be plus 150, which will equal TA minus 120. I'm gonna write this where we can say, so it will be T5 equals TA minus 120. I'm sorry, it's off.